So in this example, we've got a mass of 20 kilograms on top of the slope. And we want to find, it's going to fall, or it's going to come down the slope. And what we've got to do is, using the conservation of energy, there's a clue, calculate the velocity of the mass at the bottom of the slope. So this mass is going to go down the slope. And as it comes off the slope down here somewhere, we've got to find its velocity. Okay, so we've got 12 meters, that's the length it's going to fall down, go down the slope. 33 degree slope, 20 kilograms. We've got to use the conservation of energy. So that states that you can't destroy or create energy, it's just conserve or change its form. And potential energy will equal kinetic energy because it just changes form. So if you remember, potential energy, the potential to do work is mgh. M is mass, g is gravity, height is height, how high this object is up. And then that's potential, not moving yet. And then as it comes down the slope, it'll change from potential to kinetic. And the formula for kinetic energy is a half mass velocity squared. So in the conservation of energy, we're just conservating, is that a word? The energy changing from one form to another, potential to kinetic. As it comes down the slope, it's getting lower in height. Okay, so PE is going down, but KE is coming up. So we've got to find velocity. So the first thing we've got to find is the potential energy of this thing at the top of this slope. Okay, and we know that potential energy is mass, which we know, tick, is 20 kilograms, times by gravity, which we know is 9.81, times by height, which we don't know. Don't know that. So we've got to find the height. Now, if you look carefully, this is a triangle. So yes, Pythagoras or trigonometry, probably SOHCAHTOA. So to find the height, I'm going to draw the triangle. This is why we need to use SOHCAHTOA and learn SOHCAHTOA. That's 33 degrees in there. I've got to find this height. I don't know what it is. I know this is 12 meters. That's height, by the way, not hypotenuse. So this length of the triangle is hypotenuse, isn't it? Hype. I'll put hype. Okay. Because it says height, not hypotenuse. So the 12 meters is the hypotenuse. There's my angle. This side here is known as the opposite because it's opposite the angle and we need to find it. So H stands for height, hype stands for hypotenuse, 33 degrees. We've got to use a bit of trigonometry. Let's move this thing down a bit. So we've got opposite and hypotenuse, sine of the angle, okay, SOHCAHTOA. I don't know the adjacent, so I can't use cos and I can't use tan, but I'm going to use sine. So sine of the angle is the opposite over hypotenuse. We know the angle, don't we? The angle is 33, so sine 33 equals the opposite, which we don't know. Okay, so the opposite really is the height, isn't it? So we need to find that, divided by the hypotenuse, which is 12. Okay, don't get these two H's mistaken. So to rearrange that, I'm going to bring the 12 across. Sine 33 times by 12 will give you the opposite side. Okay, which on your calculator will give you 6.5 meters. Make sure you're in degrees. All that means is this thing here is 6.5 meters up. So now using just the conservation of energy, okay, we're ignoring friction, okay, we're ignoring the losses, okay, we haven't got to find acceleration. That's the Lambert's method, we get onto that. We're just using purely conservation of energy, difference in heights. So now I can find PE, because potential energy is mass, gravity, height. The mass is 20, I think. Yeah. Gravity is 9.81. Okay, gravity in it, acceleration due to gravity, and the height was 6.5. This will give you the potential energy of this object, the potential to do work. So that gives you in joules, because energy is in joules. 1, 2, 7, 5.3 joules. That's how much energy this thing has got at the top. Okay, that's the energy in the system. So as this object now comes down the slope, that energy is going to convert into kinetic, because kinetic means moving. So as the thing moves, it's going to increase kinetic, decrease. So I'm going to assume, don't assume a lot of things, right? Assume at the bottom of the slope, PE equals 0. It gets to the bottom of the slope, the height is 0 down here. There's 0 height. I'm assuming that. So PE is 0. So that energy has got to have gone somewhere as it comes off the slope, the precise moment. So all of the energy now, the 1275.3, is now kinetic. That's what I'm saying. That's my problem, and I can say what I want. Okay. So it's converted from potential to kinetic. So at the bottom of the slope, as it comes off, all of that energy is now kinetic, which is handy to know, because now we can use this formula here, because there's V there, look, and we've got to find V. Get him a colour pen, because I feel like I'm going to eat an orange. So we know that KE, kinetic energy, is a half times the mass times velocity squared. We've got to find V. Now I know KE. I'm going to put a tick. I know KE because it's there. I know a half. I know the mass. So I'm going to rearrange this formula now for V. Don't get scared. I'm just rearranging the formula. So KE, I leave the KE by there. I'll do it. I'm going to bring the half m down here, look, because it's both times by, so do the opposite, half times the mass. You could multiply things by 2 to get rid of the half, but I'll keep it simple. So I've just brought the half times the m down. That's got to equal v squared. We all know that the opposite of a square is a square root, so here's the formula. V is going to be square root, all of this, k e divided by half times your mass. That will give you a velocity. So V square root, just all square root, different colour pen, KE, well, I'm assuming all the potential energy from the top is coming down the hill, and now it's 1275.3. Conservation of energy, 1275.3, all divided by half times the mass of the object, which was 20. This now will give you, with all my assumptions, the velocity as it comes off here. Look, it's going to come there, look. So put on your calculator and you will get a velocity of 11.3 meters per second. Thank you very much. Velocity at bottom. Using the conservation of energy.